Alright, so yesterday we ended off with converting polar to rectangular, and what were the two functions that we used to do it? Two trig functions.
Oh, cosine and sine.
Cosine and sine. We used cosine for the x, we used sine for the
So
y.
we're going to use tangent today.
So tangent is going to be involved somehow with this, and another theorem you already know. So, this time we're going to be starting off in rectangular. When you have a rectangular coordinate, what are the two things that you know?
X and Y.
You know x and you know y, right? So, if you have this point here, that's like knowing, let me just put a line in like this. All right, put that in straight down. You have this, that's your x distance. How far to the right you've got to move from the origin to get to that point. And then you have this. That's your y distance. How far you need to move from the end of the red segment up. Right? X, y. You'll know both of those. In polar, what are the two things that you need to know?
X and Y.
Well, x and y is rectangular.
Oh,
Radius and the angle. The radius is that. So somehow you have to take the x and the y and convert it into r. There's a way to do that. If you know x and y, you can find r. Okay. Now, the angle is right there. And as long as you know x and y, there's a trig function that will tell you the angle. So you're going to be given what's in red and green, and you have to find what's in black. Okay. And I'm going to write it down nicely on the next page, but just to kind of go through it kind of quick here. If you know x and y, how could you get r? Yep, the Pythagorean Theorem. So one of the things you're going to use today is Pythagorean Theorem. That's going to give you r. And now let's look at the names of these two sides. That side is named y. Where is it? What's its position in the triangle? From the perspective of the angle. It's opposite. How about x? What position is that in? Adjacent. What trig function uses these two? Tangent. So the tangent of your angle equals opposite over adjacent. But I don't want to know the tangent of my angle. I want to know my angle. So what would you have to do to get rid of tangent? Inverse tangent. Okay, I'm going to write this down nicely on the next page. So you don't have to write it right now. I'm just showing you where the formula comes from. So inverse tangent is how you get your angle. Pythagorean theorem is how you get the radius, and that gives you both things. Pythagorean theorem, inverse tangent. Okay? So let's write that down. So, and you'll see why you have to do this, but the first thing you have to know is what quadrant your point is in. Right. So if I gave you the point like 3, -8, you don't have to know exactly where, and you don't even really have to graph it. If you can figure that out in your head, that's fine. So I'd say, okay, 3, -8, it's right there. That's quadrant 4. Okay, just a reminder, 1, 2, 3, 4. Those are your quadrants. Okay, so figure out where your point is. Once you know the quadrant, now you can find the angle. What trig function did I just say you need for the angle? Inverse tangent. If you're in quadrants 1 or 4, here and here, all you have to do is what I just wrote on the other page, the inverse tangent of y over x. The problem with inverse tangent is it only gives you an answer between -90 degrees and +90. Well, -90 is down here. +90 is up here. -90 to 90 is from there to there. It doesn't give us any answers over on this side. But you could definitely have a coordinate in quadrant 2. What if you had the coordinate -7, +5? That's left 7, up 5. So you can end up with points over here. But this formula won't work for it. So if you're in quadrants 1 and 4, that formula is fine. If you're in quadrants 2 and 3, it's almost the same formula, but you have to make like an adjustment. Bless you. So once you know you're in quadrants 2 or 3, you have to add 180 to your answer. Okay? Or pi if you're doing it in radians. So quadrants 1 and 4, it's inverse tangent of y over x. Quadrants 2 and 3, still inverse tangent y over x, but then just put a plus 180 in front of it. Or if you're doing radians, put a plus pi. Now, these two formulas cover being in quadrants 1, 2, 3, and 4. That still doesn't cover everything. Where else could you be besides quadrants 1, 2, 3, and 4?
Right in the middle.
Well, think of it like a circle. You're going to be somewhere on that circle. Yeah?
Could be on an axis.
Could be on an axis. Let's look at what happens if a point is on an axis. And let's see if we try to use one of these formulas, what would happen. What's the x value of that coordinate? 0. And the y value, I don't know. It's off a certain amount. But the important thing I want you to notice is the x value is 0. What happens if you try to use this formula and you plug in 0 for x? It's undefined. You'd be dividing by 0. You can't divide by 0. You can't divide by 0 here either. So if you're on an axis, you don't use those formulas. What do? You just memorize the 4 answers. 0, 90, 180, 270. You just have to memorize those 4. Right is 0, up is 90, left is 180, down is 270. It's the same way we've been labeling the axes all year. So 0, 90, 180, 270. Now, how can you quickly tell looking at a coordinate that it's on an axis versus in a quadrant? Yep.
Either the x or y is 0.
Right. If you're on an axis, either the x or the y is a 0. So if you've got a coordinate with a 0 in it somewhere, your answer is one of those numbers. You would never have both the x and the y 0. Because think about it, usually, well, I guess you could, but usually we're on this circle somewhere. So you have to be at a point on that circle. Usually not in the middle of it. Okay? All right. So any questions on that? So you've got the formulas if you're in a quadrant, right there. And that's what you do if you're on an axis. Okay. So that's your angle. And that's how you find your radius. Now, we said earlier, this really has a name. What's this formula? It's the Pythagorean Theorem. So x squared plus y squared equals r squared. We're not using a, b, and c because when you graph, you usually use the letters x and y. So x and y make more sense than using a and b and c. And this works everywhere. Doesn't matter if you're in quadrants 1, 2, 3, 4 on the axis. You can always use this formula. Okay, let's look at an example. So here's the point 2, negative 2. Okay, and I want to convert it to polar. All right, step 1. What's the first thing I have to know about that coordinate? Yep, what quadrant it's in. What quadrant, you don't even really have to graph it, but what quadrant is it in?
4.
Yeah, 4. Somewhere right around there. Right 2, down 2. Now, whether you find the angle first or you find r first, it doesn't matter. They're totally separate. Let's do the angle. So, when you're in quadrant 4, is that a quadrant where you have to add the 180?
No.
No. So what's the formula for quadrant 4?
Inverse tangent. Negative 2.
Of y over x. Negative 2 over 2. Now, just to save time when I type it in, what's negative 2 over 2? Negative 1. Right? So I'm going to do the angle in degrees. Question didn't say to do it in degrees or radians, so I'm going to pick degrees. Inverse tangent. Negative 2 over 2. You could have just typed in negative 1. you get an angle of negative 45. So that's the first thing you need. So now we've got an angle. Now, I could write that as a positive. We'll talk about that after. What formula do I use to get my radius? Yeah, and can you plug it in for me? Tell me, Aaron, what it would be.
R squared
Yeah, r squared.
equals 2 squared.
2 squared.
2 squared plus negative 2 squared.
All right. So 2 squared gives me how much?
4.
4. Negative 2 squared?
4.
4 again. So r squared is 8. So what's r?
Square root of 8.
The square root of 8. Or 2 square roots of 2, if you reduce it. Okay, so let's write we'll write our answer. So the answer is r, comma, theta. Now, the way I did the answer, I did a positive radius, I did a negative angle. How many ways are there to write an answer in polar? 4. Okay, there are 4 different ways. So, just roughly eyeballing it, I'm not doing the radius exact, I will do the angle. Negative 45 is about right here. So we just did this. That. I'm not going to write all 4 ways, we did that yesterday. Let's just write one other way. What if I wanted to go this way and go around the other way to get to that point? How could I write it that way? The angle would be 315. Yep, that's what we did yesterday. So angle is 315. What about the radius? Yeah, it would stay the same because I went to the right. Okay, so there's 2 different ways you could write that answer. I tend to like positive. I like both numbers positive. But there's nothing wrong with positive, negative, unless the directions say not to do that. Okay. Any questions on how we got the first answer or how we changed it to get the second one? All right, let's try this one, convert to polar. All right, so negative 4, comma, negative 5. All right, what quadrant is that one in? 3. It's left and down, so it's somewhere in the 4th quadrant. All right, what is my formula to find the angle if I'm in the 4th quadrant? And let's do it in degrees.
So it's 180 plus the inverse of tangent, whatever it is.
So 180 plus the inverse tangent of, now what are you taking the inverse tangent of? Negative 5 over negative 4, which you could just write as 5/4. Because the negatives cancel. Okay, that's not going to come out to a nice number. So we're just going to type that in and see what we got. Inverse tangent of 5/4. I should have put the 180 in front of it, but I can just do plus 180 now. That's fine. So 231.34. That's my angle. Okay, so I got that. And Aiden, can you help me get my radius? All right, do you have the formula written down for the radius? It was step 3.
I do not.
Did not. Anyone help me out, Caleb? Yeah.
4 squared plus 5 squared.
4 squared plus 5 squared. Anything else?
R squared.
Yep. So that's going to give me 16 plus 25. What's 16 plus 25? 41. But now I want r, so I'm going to do the what on both sides? Square root. So r is the square root of 41. Now, normally I would leave that as an exact answer, square root of 41, but I already rounded the angle. So let's just round everything at this point. Okay. So if you round one thing, just round everything then. So square root of 41. Did I move that? Oh, that's weird. Sorry. So square root of 41, 6.40. Okay, so the answer, r, comma, theta, 231.34. And there are three other ways to write that answer, but I usually prefer the positive. Okay, any questions on that one? Okay, so that finishes up 5-1. That's all that was left in that one. Yeah.
So you just take the positive value of your original coordinates, like -4 and -5, you just did +4 squared plus +5 squared.
You're right. Technically, I should leave the negative in there, but because I'm squaring it, the negative doesn't matter.
Oh yeah, it doesn't matter. Yeah, it's a negative.
Yeah. I mean, technically, it's important when you do the inverse tangent.
Okay.
Because the negatives aren't being squared there.
Right.
But when you're doing Pythagorean theorem, whether you use the negative or not, it's going to cancel.
Okay.
So, -4 squared is 16, -5 squared is still 25.
All right, makes sense.
So, yep, that's important. Any other questions on it? Okay. So, let's look at our second part. And actually, before I even look at Appendix 4 in the back of the book, I'm just going to kind of put the appendix into context, like what we're doing, why we're doing it. So, what I want to do is just make a quick chart of numbers, okay? Different types of numbers you work with. So, each one of these boxes is going to have a name, okay? And as we expand out, it's going to get broader and broader. It's kind of like, pretend this central box is very specific. Boston, okay? And then a little bit broader, Massachusetts. And then a little bit broader, the Northeast. And then a little bit more, the United States, okay? So each time we put a new name, it's going to include more stuff. Okay? So this one in the middle is going to be the smallest, okay? And it's the simplest kind of numbers we can work with. Think of like kindergarten. What kind of numbers do you work with in kindergarten?
1.
Okay, what else?
1 through
2.
10.
1 through 10, sure. What are those kind of numbers called?
Real numbers.
What's that?
Real numbers.
That's going to be the very last, well, second to last thing we do. That's like almost the most complicated thing we have. So, whole numbers is going to include one more thing that we don't normally include. Whole numbers include this extra number, but what number do you think we're not going to include because it's too complicated?
0.
0. We're not going to include 0. We're just going to include 1 and up. And what can you do with numbers that go from 1 and up? Like the simplest thing you could do.
Add them.
You can what?
Add.
Add them? Okay, what else?
Subtract.
Well, even simpler than doing arithmetic. No arithmetic.
You can write them. Oh, count it.
Count them. Just count. 1, 2, 3, 4. Right? Those are your counting numbers. Simplest kinds of numbers there are. The problem with counting numbers or any of the number sets we're going to look at is when you start doing arithmetic. Now, if you take somebody give me a counting number. Any counting number that you can think of. 5, right? Another counting number?
7.
7. So counting numbers don't include fractions. Like when you count, if you're counting objects, you don't count like 1, 1.5, 2, 2.5, 3. You don't use negatives, and you don't start with 0 when you count. You don't go 0, 1, 2. You start 1, 2, 3. So counting numbers don't include 0. They don't include negatives. Don't include fractions or decimals. If you add 5 plus 7, what do you get? 12. Is 12 a counting number?
Yeah.
Sure. If you were counting things, you might come across the number 12. Now, let's look at another operation. Let's look at subtraction. That's a problem. Okay? Subtraction is something you are allowed to do with numbers. But if all you understand is counting numbers, when you try to do 5 minus 7, you would have to write undefined. You'd write undefined because there's no such thing as negative. Negative doesn't exist in your world. Okay? Counting numbers, only 1 and up. So never mind that, you can't even do this. If you tried to have 3 take away 3, you'd say undefined. You can't do that because there is nothing that exists unless we invent something that exists. And they invent the number 0. Right? And those are called your whole numbers. So what whole numbers basically do is invent the number 0 and give you a way to write this as an answer. So now if you have 3 minus 3, you don't have to write undefined anymore. You have a special symbol, and it looks like this in math. It's like a circle, and it represents the idea of nothing. Okay? But let's get back to this one. If you did 5 minus 7, is that a whole number? No. Whole numbers include 0 and up. No fractions, no decimals. So if I gave this to somebody in like maybe 1st or 2nd grade, they wouldn't know what to do with that. They'd be like, well, I can do 7 minus 5, but not 5 minus 7, because this represents the idea of having even less than nothing. So the symbol that we use for that is we put that little symbol in front of a number. For whatever reason, somebody decided that that little dash like that is going to represent a number that's even less than nothing. So it's negative. And I heard somebody say the type of numbers earlier. Does anybody know what the next set of numbers are that now include your negatives? Integers, yep. So now with integers, addition and subtraction are not a problem. If you give me any 2 integers, I can add them, and I will always get an answer that's an integer. If you give me any 2 integers, I can subtract them, and I will always get an answer that is an integer. I'll never get something weird that I don't know what to do. How about multiplication? If I multiply 2 integers together, will I always get an integer? Yes. There's no way to get a fraction if you multiply an integer times an integer. How about division? Could I run into a situation that I'm like, don't know what to do? What could happen when you're dividing? Give me 2 integers that would be a problem to divide. 7, okay. 7 divided by 6. So now what you're telling me to do is basically take 7 objects, or say I had 7 pens, and give them equally to everybody. I can't. I can't take 7 objects and give them out to 6 people equally. The only way I can do that is I start breaking things into pieces, parts of things. All right. So again, somebody in like 1st or 2nd grade, they'd probably just put a question mark. They wouldn't write undefined, but they'd put a question mark. They wouldn't know what to do. There's no way to do that unless you invent having parts of numbers, and those are called your rational numbers. So now with rational numbers, you can pretty much do everything you would need to do like in everyday life. Most people don't need to understand much beyond rational numbers. Like when you buy something at a store, okay? Most of the time when you buy something, it's going to come out to a certain amount of dollars and then a fraction of a dollar. I mean, maybe it comes out exact, but a lot of times it might come out to like $12.58. That 0.58 is a fraction. It's 58 hundredths of a dollar, right? It's part. When you're cooking, maybe you need, 2/3 of a cup of something. You don't need a whole cup, but you don't need like 0 cups. You need something in between. You need part of a cup, 2/3 of a cup. So if you're in like a machine shop and you're machining a part, maybe you don't have to machine it to be 1 inch or 2 inches. You need it to be like 1.645, 1 inch and 640.645 inches, right? So it's fractions of an inch. Right? So again, that's what you need for pretty much everyday numbers. Now, let's look at this. Square root of 2. Square root of 2 is impossible to write as a fraction. It's not like I'm saying we don't know how to do it yet, and maybe someday we will. No, we never will, because it can't be done. It can be proven that you can't do it. So there's ways to prove that you will never be able to do something in math. No matter how good computers get, you'll never be able to write that number as a fraction. So it's the opposite of rational. Does anyone know what those are called?
Real.
What?
Real.
Real? Not quite. Irrational. So irrational numbers are numbers that we've invented a name, because otherwise, how could you can't take the square root of 2. If all you believe in is rationals, and you say, okay, I believe in rationals, that means I believe in fractions, then there would have to be a way to write this as a fraction, and there's not. So you'd say, oh, it's impossible. You can't take the square root of 2 because you can't write the answer. Well, no, you can write the answer, but you have to use another kind of number to do it. It's called an irrational number. So that's irrational. Numbers like pi, that's irrational. Okay, basically, square roots are where you see irrational numbers a lot. Okay? The square root of anything that doesn't come out nice. Square root of 4, well, that's different. That's just 2. Square root of 9, that's just 3. Square root of 6, square root of 7, square root of 8, those are all irrational. And now, if you take all the rationals and irrationals and put them together, what kind of numbers do you get? Those are your reals. And in Algebra 1, that's what you study. When you solve equations, when you do quadratics, when you factor, everything falls into that category right there, reals. But when you get to Algebra 2, you learn that there is a problem with reals. This is the problem. If I wanted to take the square root of a negative number. Why would you take the square root of a negative number? Well, applications for this, very advanced. They're not the kind of things most people do in everyday life. Right? We're not really going to look at applications. We're just going to look at, okay, how would you do the problem? The applications would probably involve calculus and up. Okay, they're pretty hard stuff. So, square root of negative 4. I want to multiply two numbers together and get a negative. That's what that says. And when you take a square root, the numbers have to be the same. So like the square root of 9 would give me 3, right? Because 3 times 3 is 9. Or negative 3 times negative 3 is also 9. So if you multiply two numbers that are the same, they could either be a what and a what. Like, think of the sign of the numbers. They could be a positive and a what? No, got to be the same. So if you're going to take a square root, you can multiply two numbers that are the same, and they could either be a positive and a positive, or a negative and a negative. They can't be different. That's not how you take a square root. They have to be the same number. If you multiply a positive and a positive, will you ever get negative 4? If you multiply a negative and a negative, will you ever get negative 4? So somebody in Algebra 1 would say, undefined. You can't do that. Okay, let's try it on the calculator. Let's take square root of negative 4. Calculator's not saying that it can't be done. Okay, it's actually giving me a pretty precise message here. It's saying that the answer is not a real number. The answer does not fall in this category. So, just like you couldn't do 3 minus 3 because it was a number that didn't exist, invent a number that exists. Call it 0. You couldn't do a negative number, so invent this little symbol to mean negative numbers. You can't do the square root of negative 4, do the same thing. Invent something that represents the answer as long as everybody uses it. It's not like you can say, well, I'm going to do it this way and I'm going to do it this way. We all have to agree on how to do it. And what we all agree on is what's called imaginary. So imaginary numbers, it's just another symbol that we've invented, like the 0, like the little dash, like the fraction bar, and the symbol we invent here is an I. Okay? So the answer to this kind of problem, if you want to think of the square root of negative 4, it's kind of like the square root of 4, but we have to say, wait, something weird happened because we took the square root of a negative. So we're going to put this little symbol next to it, I. Okay? So it's just a symbol that we invented. That's all it is. And when you take all your reals and imaginaries and put them together, you get the biggest set, which is called complex numbers. Now, if you're asking, is there anything beyond that? Like, is there any kind of calculation you could try to do where the answer wouldn't be a complex number? There's something even more advanced. I'm not really aware of anything more. Right? That's all that I really know about. And the reason I kind of gave you locations like Boston, Massachusetts, Northeast, United States, is because if you think of that chart that way, it helps it to make sense. If you're in Boston, are you in Massachusetts?
Yeah.
Yes. If you're in Massachusetts, are you in the Northeast? Yes. Now, if you're in the Northeast, are you in Massachusetts?
No.
Not necessarily. So the way this chart works is if you're a counting number, you're automatically a whole number. If you're a whole number, you're automatically an integer. But if you're an integer, you're not automatically a whole number. Okay? Just like the places. Okay? As you expand out, each set of numbers includes the one that came before it. Just like if you expand to the Northeast, that automatically includes the Massachusetts. If you expand to the United States, it automatically includes the Northeast. Each set always includes the ones below it, but not the other way around. Okay? So, what's that?
Irrational numbers we Canada.
Well, I'd have to start with a city in Canada instead of Boston.
No, it's Canada. Irrational would be Canada.
Why?
Because they're attached to the U.S.
Well, you have to get bigger each time and encompass what came before.
Okay.
So-
Mars.
So if you,
Earth.
well, you could do Earth. You have to encompass everything below it. You can't, you know what I mean? Kind of like those, what do they call those? Those dolls that have like the dolls inside them? The Russian dolls. The biggest one includes all the ones below it, but not the other way around. The little one doesn't include the big one. The big one includes the little one.
So is imaginary like the moon?
Imaginary? Imaginary, yeah, that one's kind of separate.
Pluto.
So if you think of reals as like Earth, and you think of imaginary as Mars, you can think of complex numbers as the solar system. They're both in the solar system. Okay? So yeah, imaginary is kind of separate. Or if you wanted to think of reals as the United States and imaginary as Canada, then complex numbers would be like North America. It would include both the United States and Canada. So that's how they work. So that's a good place to start. Complex numbers. So when we write complex numbers, they have two parts. And I just showed you the two parts. Complex numbers have a real part, and they have an imaginary part. A is the real part, and A would be a number, like 5, 2/3, 0.7, right? -12, something, right? A has a real part, and B is the imaginary part. Now, when you write it in that order, real part first, imaginary part second, that's called standard form. Anytime we have to do a calculation, whether it's, we're basically going to do 4 things: add, subtract, multiply, and divide. We're going to do add and subtract today, multiply and divide tomorrow. Okay, when we do those, I would like your answer in standard form. Okay, so it should look something like that. That's standard form. In this case, 2 is the real part. 3 is the imaginary part, not 3i. The I is just there to tell you what's next to it is the imaginary part. Okay, and I think if you just think of complex numbers as calculations we're doing, That makes it easier. If you try to understand the applications of complex numbers are very like high-level stuff. They're not simple. It's very, very like way beyond stuff that I do. Okay, way advanced stuff. Good. So any questions on what standard form means? All right. So if a number doesn't have a real part, say the real part is 0, that's called a pure imaginary number. Those are examples of pure imaginary numbers. 4i. Technically, you could think of it like this. 0 plus 4i. There is no real part. When there isn't a real part, we usually just leave it off. We don't write it. We just put 4i. Now, one thing that can be a little confusing when you're doing this, if your i's look like 1s, you might trip yourself up and say, oh, I got the number 41. Try to make it pretty clear that your i's are i's. It would be very clear, I think, if we used a capital I, but they don't. They don't use capital I. It's always a lowercase. But if you make your 1 like this, then it's really clear that that's a 1, and that's an I. Okay, so I'll try to make sure I do that. Okay, so that's a pure imaginary number. Okay. Now, anytime you invent a new number, and I'm sure I know you guys probably go home and do that a lot, just invent.
Awesome.
Yes. So anytime you invent something new, you can't assume that it works the same way that the stuff before did, right? Well, they invented this number 0. Before that, they knew about the numbers 1, 2, 3, 4, 5, 6, 7, 8, all the way as high as they want to go. But now that they invented 0, some rules might change. Like weird things might happen. Like, I wonder when they invented 0, if they ever thought about what happens if you divide by 0. Well, we never had that problem before because we never had 0. Now we do. Well, we can't do that. So what would we tell people if that happens? Well, today we just say undefined. We just say you can't do it. So when you invent something new, you got to check and see if, okay, now this brand new thing, does it play well with everything else that came before it? Does it still work the same way? So you can't assume that adding, subtracting, multiplying, and dividing work the way you would think they would work anymore, because we're using imaginary numbers. It turns out that it pretty much does work the way you would hope, right? It's not really weird. It's pretty common sense. But there are some things in math you gotta double check when you invent something new. Does it still work with everything else that came before it? Right? So what does it mean for two complex numbers to be equal? Well, usually when two numbers are equal, we just look at them like this. There's one thing I compare on the left, there's one thing I compare on the right, and I say, okay, in my brain, I look at those two symbols, and I say, does that symbol look like that symbol? If the two symbols look the same, then they're the same. With imaginaries, there's one extra step. I have to look at this symbol on the left, and then I have to look at this symbol on the right, whatever numbers they actually are in my problem. And I have to check if those are the same. But that's only half of it. Then I have to check this symbol on the left and this symbol on the right and see if those are the same. So it's just really, it's a little bit more work. I got to check two things instead of one thing. So check that A and C are the same, and then check that B and D are the same. So an example of two complex numbers that are equal, very simple idea. Check that this number and this number are the same. Yep, they are, but you're not done. Check if this number and this number are the same. Yes. The real part on the left matches the real part on the right. Imaginary part on the left matches imaginary part on the right. That's all it is. So those are the same. Those numbers are equal. Now, if I did something like, let's take this example and go like this. Are those complex numbers equal?
Numbers are exactly.
Not exactly the same. The real parts are equal, 3 and 3, but that's not good enough. The real parts have to match and the imaginary parts have to match. They don't. One is positive 8 for the imaginary, the other one is negative 8. So they're close, but they're not equal. Only part of them is equal. Okay. Now they're equal. Right. Any questions on that idea? All right, so sum of complex numbers. When you're adding complex numbers, you basically want to think about it as combining like terms. Okay? You can only combine real numbers with real numbers. You can only combine imaginary numbers with imaginary numbers. So like I had something like 2x plus 3y plus 4x plus 8y. I can combine some things there, but only certain things. I can combine this with that. That's okay. I can combine this with that. So I would end up with 6x plus 11y. Now, can I combine 6 and 11 and say 17?
No.
No. Why not?
Because one's an X, one's a Y.
One's an x, one's a y. They're not like terms. Okay? Same thing with a real and an imaginary. One's a real, one's an imaginary. You can't add 3 plus 8 and say 11. That's real, that's imaginary. They don't go together any more than that. So, to add complex numbers, the way you do it, take the real part here, take the real part here, and combine them. A plus C. And I'm doing plus because we're doing sum. We're going to do difference after. All right? So take A plus C. Combine them. Now, take the number for B, take the number for D, add them together, but you've got to put an I next to it so the person reading it knows that that's the imaginary part. B is imaginary, D is imaginary. Add them together and put the I to remind me, yeah, they're imaginary. And that's it. That's how you add complex numbers. So it's just like combining like terms. So let's look at this. 3 plus 8i plus 8 plus 2i. Okay. The way it's going to be set up on the test is you're going to have 4 problems from what we're doing right now and the beginning of tomorrow. One add, subtract, multiply, divide. One of each. Okay. This is an example of it. So what's the real part in the first complex number? 3. What's the real part in the second complex number?
8.
And combine them together to get a final real part of how much? 11. So we get 11. Now, what's the imaginary part from the first number? 8. Imaginary part from the second number?
2.
And when you combine, specifically when I say combine, I mean add this time. 8 combined with 2 gives me 10. And what do I have to put with it? An I, so we remember that it was imaginary. So 11 plus 10i, and that's your answer. Any questions on that? Let's look at another add. Right, 4 minus 2i plus 3 minus 8i. Okay. When I add these together, even though you can't see the directions anymore, just look at the symbol right there. It's add. What's going to be the real part? 7. And what's going to be the imaginary part? Negative 10. And then put the I with it. And you're done. So that's negative 10i. So sometimes it's a plus, an imaginary number, sometimes it's a minus. It depends what you're adding. Right? When you do regular addition, sometimes you get a positive number, sometimes you get a negative number. Right? And last one before we look at subtraction is this. Negative 3 minus 4i plus negative 7 plus 8i. Okay. What's going to be the real part when I combine these together? Yep, so negative 3 plus negative 7 gives me a negative 10. And what's going to be my imaginary part? Yep, negative 4 combined with a positive 8 gives you 4i. So, any questions on addition? Addition and subtraction it's pretty much the same thing. Okay, just you either add or subtract. So when you subtract, think of this negative as being distributed. So when you combine these together with subtraction, you're going to do A minus C. That's the first thing we do. A minus C. And the second thing, B minus D. What some people forget is to subtract both. So subtract the reals, then subtract the imaginaries. A minus C plus, and then do B minus D. Now, this plus might turn into a minus. It depends on the problem. When you do subtraction, sometimes you get a positive answer. When you do subtraction, sometimes you get a negative answer. It just depends on the numbers you use. But what you do have to make sure is you put this I after you do B minus D. Same rules apply here as if you were doing subtraction with real numbers. If you minus a minus, it becomes a plus. That doesn't change. That rule still works. So let's try to subtract these. 4 plus 12i minus 3 plus 4i. Right, so Peter, if I subtract these two complex numbers, what's the real part going to be in my final answer?
You see, you have to like distribute the negatives. So.
Yep. So what's the real part in the first complex number? 4. And what's the real part in the second thing that's in parentheses? 3. And now you're subtracting the 2.
Yeah,
1. Yep. So yeah.
Did I say negative 1?
I'm not sure.
Maybe, I don't know.
Yeah, I don't know. We'll check the tape.
I thought I said, yeah. I thought I said 1. Negative.
So positive 1. And now, what about my imaginary part? What's that going to be? 8. Positive 12 minus positive 4 is positive 8. And what do I put with it? I. So 1 plus 8i. Right, let's, I think I got one more subtraction. Yeah, one more subtraction. All right, so we got 3 minus 5i minus 8 minus 6i. Ben, what's going to be my real part when I subtract here?
Negative 5.
Yeah, negative 5. And now be careful with the imaginary part.
11.
No, not 11.
Negative 11.
What's the imaginary part in the first one?
Oh, would be negative, not negative 1 or...
Well, what's the imaginary part in the first number?
Negative 5.
Negative 5. And what are you subtracting?
Negative 6.
You're subtracting negative 6.
Oh, it's 1. So you're adding.
So you're adding 6. Negative 5 plus 6. 1. 1 what?
I.
When it's a 1i, you can put 1i, or just like in algebra, we can put I. Okay, you don't have to put the 1. If you put the 1 in front of the I, it's fine. Alright. But be careful, because on a problem like that, if it was a multiple choice, I'd probably give you all the things you said. 11, negative 11, negative 1, but it's really positive 1. I. Alright, so we've been writing this I thing the whole time. We just keep writing I. It's like this thing we invented. Well, I is defined to be the square root of -1. That's what I is. If you want to say, okay, well, what number does it really mean? That number. Why? Why is it that number? Because it is. It's a definition. I equals the square root of -1. I can't explain why. I can't prove that to you. It's kind of like if you said to me, well, why don't parallel lines cross? Because they don't. Why? Because that's the definition of the word parallel. It means lines that don't cross. I cannot prove to you why parallel lines don't cross. They don't. I can't prove to you why I equals the square root of -1. That's just what it is. So, as long as everybody agrees on the same thing, it's like as long as we all drive on the right side of the road, we're okay. If we don't follow the rule and everyone decides to do their own thing and say, I'm going to let I be 5 today, then we have problems. So, I equals the square root of -1. We all agree. We all do it. That's what it is. So, because we all agree that I is the square root of -1, that means all kinds of things now. In particular, it means something about I squared. Okay? If we're going to say I is the square root of -1, then we can say I squared is something. What does I squared mean? Like if you had to write it out.
I times I.
Right, it means something times itself, right? Or you could also write it like this. The square root of -1 squared. I squared. That's I squared. What happens when you square root and square something?
It cancels each other out.
Square and the square root cancel each other out. And what's left? -1. So if we all agree that I is the square root of -1, then that makes I squared something very nice. It makes it the number -1. So why is that important? Well, when we do multiplication and division tomorrow, I squared is going to come up a lot. Anytime I squared comes up, if you leave it in the final answer, you're wrong. I squared should always be changed to the number -1. Always. Okay? It's kind of like if you left something like this on a test. 3, 6, you can really simplify it, right? You can reduce it to 1/2. It's the same idea. I squared can be simplified to the number -1. Okay. So, any question on that? So that's what we'll pick up with tomorrow.
I had a question just about the complex numbers. So we're basically just combining like terms for those?
It's like combining like terms. Yep.
Okay, sounds good.
Yep. Now, I know I'm saying to you, think of it as combining like terms. Now, when I use I in math, that's not a letter. Yes, the symbol is a letter, but it stands for the number that I just circled. Right? Just like if somebody knows Greek. Is that a letter in the Greek alphabet?
Yep.
Then what is it? Yeah, it's a letter from the Greek alphabet. It's their letter. Pi. It's okay. So that's a letter from the Greek alphabet. When we use that letter, when we use this symbol in math, is that a letter? Or does it stand for something? It stands for a number. So you would never do math and say, let that be a variable. Why would never? Because this symbol means something. It means this number. That's why in math, you generally wouldn't use I as a variable because it means something. It stands for that number. Okay? So even though we're using the English letter I want you to understand it doesn't mean a letter. It's just the symbol that means that number. Okay? Just like that letter in Greek, it's not a letter in math. It stands for the number 3.14. Okay? Same idea. Okay, any other questions? Okay. So homework from 5.1, the first part, it's 308, 55 to 65 all. And then the second part is on adding and subtracting complex numbers, page 560, 9 to 14 all.